Hello, everyone. Now let's just do a ton of examples of computations of derivatives using the formal definition of the derivative. So my next example is we're going to compute together the derivative of the function minus 2x squared plus 4x plus 3, and then we will use this derivative to compute the slope of the tangent line at x equal to 0. Again, any solution starts with the limit definition of the derivative, so the formal definition. So f prime at a is equal to the limit as h goes to 0 of f of a plus h minus f of a over h. Every single solution starts like this. And now the first thing to do is simply to evaluate our function at a plus h and at a and subtract the 2. So here we go. So this limit becomes the limit as h approaches 0. So my function is minus 2x squared. So the first thing you do, just open a big bracket here, minus 2. So x, every single x is replaced by h. So you get minus 2 times a plus h in a bracket squared plus, okay, here we go, plus 4x, where now x is replaced by a plus h plus 3. So that's my evaluation. Really to stress this fact here. So I'm replacing every single x by a plus h. So you can follow here the evaluation process, and then you subtract. So then it's minus f at a. So you replace every single occurrence of x by a. So you get minus 2 a squared plus 4 times a plus 3. So again, to illustrate that, so all my x's were replaced by a in my second term. And then all that is over, let's draw a straight line here, it's over h. Now this is the part where you FOIL and simplify as much as you can. So here I will do two things with the minus 2 times a plus h squared. So when you square a plus h, we know it's a squared plus 2ah plus h squared. Oh my God, I have a hard time saying that. And then I multiply by minus 2. So here, if you FOIL and you multiply by minus 2 at the same time, you get the limit as h goes to 0. So you get minus 2 a squared. So I'm FOILing and multiplying by minus 2 in one move. Then you get plus 2ah times minus 2. So you get minus 4 ah plus h squared times minus 2, which is not going to be a plus but a minus, sorry, minus 2 h squared. Now let's multiply by 4. So you get 4a plus 4h plus 3 alone. And then the only thing you have to do with the second bracket is just multiply everything inside by minus 1. So you get plus 2 a squared minus 4a minus 3. And all that is over h. And this is very typical in these questions. Everything inside the bracket for f of a will typically cancel with something on the other side. So for example, here I'm going to use my marker to cancel terms. So this minus 2a squared, so this minus 2a squared will cancel this plus 2a squared. This 4a here will cancel the minus 4a, and the 3 here, the plus 3, will cancel the minus 3. And then what you're left with is a bunch of terms, and all the terms that remains, they will all have an h that you can factor. So you see here the minus 4ah, there's an h here, minus 2h squared, there's an h, the 4h, there's an h. So we have 3 terms where there's an h, so you can factor by h. So now my limit will become the following. So if you cancel all the terms and then you factor by h, you're going to get h up front. So you get minus 4a minus 2h plus 4, all that over h. And then, of course, that's the nice aha moment, okay, where you simplify you cancel the h from above and below. And this is always the end game of these questions. You want to cancel the h below somehow. So here, the h that you just freshly factored will cancel the one below. And then you'll be left with a brand new expression So this is, of course, the old principle part. So I like to write that one down. So limit as h goes to 0, you get a brand new expression. It's different, but it will have the same original limit as the previous one. Now you can evaluate. So let me just write my Holyoke principle. This is my obsession. If you don't write that down, you're fine, okay? Or if you're cheating on me with another YouTuber, okay, they're probably not. Well, I'm not a YouTuber, but what did I just do there? Maybe I'm accepting my fate here. Anyways, so if you don't write down the HHP, it's fine. So now I'm evaluating my limit. So the limit notation is gone. I get minus 4a minus 2 times 0 plus 4. This will give you minus 4a minus plus 4. So that's your derivative. So f prime at a is minus 4a plus 4. Of course, if you already know the rules of differentiation, okay, you can get this formula pretty quickly in your mind. But anyways, we don't know that rule yet. Okay, so now if you want f prime at x, you just replace all the a's by x. So you get minus 4x. Let me just change color here. Sorry. Minus 4x minus 4x plus 4. That's my f prime. And now if I want f prime at 0, I just need to evaluate at 0. So you get minus 4 times 0 plus 4, and you get 0. So if we were to draw that parabola, minus 2x squared plus 4x plus 3, and we wanted to compute the slope, not 0, sorry, 4. Let's go to 4. So if you were to compute the slope of the tangent line of this parabola at sorry, not if you were, like the slope of the tangent line of minus 2x squared plus 4x plus 3 at 0 is 4. All right, let us do another example. Let's compute the derivative of f of x equal to x cubed, and then we will use the derivative to find the slope of the tangent line at x equal to. Again, the solution always starts the same way. F prime at a is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h. And now what we want to do is replace these f's by their function. So here, if my input is a plus h and I'm cubing it, I'm going to get the following. So we get the limit as h goes to 0. So here, if my input is a plus h, I'm going to get a plus h to the power 3. So my input a plus h is replacing x here. So we're getting a plus h cubed, and then minus a cubed. So replacing my a here for x, so it's a cubed, and all that over h. A plus cube quickly. Okay, so you might remember it. If not, I'm going to recall it for you. So a plus h cubed quickly is a cube plus 3 times a squared h plus 3 times a h squared plus h cubed minus a squared. A cube, sorry. All that divided by h. And now this is where the magic happens. So this a cube here simplifies this minus a cube, and then you're left with 3 terms, and all these terms, they have an h. So I can factor by h, so you get the limit as h goes to 0. So h goes up front. You get 3a squared plus 3ah plus h squared, all that divided by h. And now, yes, we have this simplification of the 0 over 0 here. So we're getting a brand new equation thanks to the old principle idea. You can simplify here, okay, and cancel those h's. It creates a new expression, but this new expression will have the same limit, so everything is cool. So you get 3a squared plus 3ah plus h squared. Now you can evaluate at 0. You get 3a squared plus 3 times 0 plus 0 squared, which gives you 3a squared. So if you want to compute the slope of the tangent line of x cubed at the point A, it's going to be 3a squared. So this means that the derivative function is simply by replacing a by x here, it's 3x squared. And now if you want the slope at 2, you just need to evaluate. So you get 3 times, sorry, I'm just going to change. So you're just going to get 3 times 2 squared, which is 12. Et voila. Okay, so we got our slope of the tangent line at 2 to be 12. All right, there's another example, but I'll just leave it to you as an exercise to compute the derivative of 2x cubed minus 3x squared plus 6x minus 6, and then to find the slope of the tangent line. This one is a bit longer, but it's not more difficult. It's just a bit more annoying. Anyways, go through it, and that closes that section, and that ends also this video. So where we did some examples of computations of derivatives using the formal definition. All right, I messed up my ending a bit. But anyways, for that section, bye-bye là. Actually, it's just a joke. We're going to continue. So we're going to talk about something critical. Critical points. Here we go. So section 4.4, critical points. So why do we care, about derivatives? So it's not just, hey, here's the slope of the tangent line and of a function at a point. Derivatives are going to be an essential tool to study the shape of a function. And the end game of Calculus 1, the biggest question that you'll ever face, on a test in calculus will be to construct the graph of a function using the domain, the important limits, and the sign table of the first and the second derivative. So the next theorem makes a link between where is a function going up and where a function is going down using the sign of the slope of the tangent line. So if you have a function and you have a point A in the domain, if f prime is strictly bigger than 0, then the function is increasing at that point. It's going up. If f prime is strictly less than 0, the function is decreasing. And this is supposed to be already seeding the idea that if you construct the sign table of the first derivative, or of f prime, then you're going to get the intervals where the function is going up or going down, associated to the plus and the minuses, respectively. But then what happens if f prime is not strictly positive or negative? So it's a limit computation, so it could give you 0, or it could give you something, or it could give you a non-real number, so the limit could be does not exist. So what happens in those cases? Well, there's a nice definition just for those special points in the domain of f, such that f prime is 0 or f prime does not exist, or where the function f prime of x is undefined at a. And these points are called critical points for the function f of x. So a critical point is a point inside the domain of f such that f prime is 0 or f prime does not exist. And visually, if you have the graph in front of you, again here I'm really obsessed with understanding what's going on visually first, because the goal is to build that visual representation of a function when it's given to us algebraically. So what does it mean f prime is 0? So it means that the slope of the tangent line is 0, which means that these lines are horizontal. So f prime of a equal to 0 corresponds to horizontal tangent. And I have an example here of a function in blue where at C or at D, my derivatives are so the slopes of those tangent line are 0. So you can see that these tangent line are horizontal. What happens if f prime does not exist? Like, how can we see those points inside the domain of x where f prime does not exist? Well, there's 3 types of points on the graph where the function f prime does not exist. If you have a corner, the derivative does not exist there. And the reason why it does not exist here, there's a couple of ways to see this. If you're really into physics, you could say, well, if you're writing the graph here and you're approaching f from the left side, and then suddenly the icy road, lets your car go, then you're going to follow a tangent line on one side, but you're not going to follow the same tangent line on the other side. So if you're writing it from the other side, you're going to go and follow a different tangent line. So there's this ambiguity here. It's not the same slope on the same side. Another way to say this is that if you were like to zoom around that little corner, you will always get a corner. And meanwhile, if you zoom anywhere else, you're going to get a straight line. So if you see a corner or a pipic, okay, on your graph, there's no derivative there. It does not exist, even if it's nice and continuous and defined. Of course, if the function is not continuous, then there's no derivatives. Here, there's like again, think about the physical representation of the physical intuition behind a slope of tangent line. If you're approaching from the right side, the point A, and you're going off road, and if you're approaching A from the left side and you're going off road, I'm not sure if I said left twice, but anyways, you have two different tangent line, so it's completely messed up. And there's another one that is kind of tougher, and people tend to miss that one, is if you have a vertical tangent. So remember, when we're talking about slopes, we're talking about linear equation of the form mx plus b. So m needs to be a positive number, and n it's not a positive number, it needs to be a real number. But when you're thinking about linear equations, they need to be equations, and they need to be, sorry, when you're thinking about linear equation, they need to be functions. And to be a function, you cannot be a vertical line. So, but when you're looking at graph, it's possible that the function is nice and continuous with no corner. But when you're following the tangent line, you get a vertical tangent. And of course, what is the slope of something vertical? Well, there is no slope, so it does not exist. So if you have a point on a graph where the tangent is a vertical line, so we call this a vertical tangent, not the same thing as a vertical asymptote. That would be corresponding to a point where it's not continuous. But if you have a vertical tangent, the derivative does not exist. So anyways, three cases: corner, point where it's not continuous, or it's where it's discontinuous, and when you have a vertical tangent. Those corresponds to f prime does not exist, or where the derivative is undefined. So let's just do an example, a visual example to finish this section. So on this graph here, on this function defined visually below, let's find the critical point, and let's find where f prime is strictly bigger than 0 and where f prime is strictly less than 0. So let's start first with the critical points. So remember, there's two types of critical points. First, let's find the points where f prime is equal to 0. So here I see only one point on this graph. It's around here where the tangent line is horizontal. I would say it's around 0.8. So here x equal to 0.8. There's no other horizontal tangent for that function. So now if we look at f prime undefined, so let's find a corner. So there's a corner here at x equal 2. That's a corner. So x equal 2 is a corner. And the function is not continuous at -1. So maybe I'll write that down so that you can study it. So x2 equal 2 is a corner. X equal -1. The function is not continuous there. So f prime does not exist, or it's undefined. And so it's a critical point too. And there's no, okay, so there's no vertical tangent for that example, sadly. Normally on a test, you will always have, like if we are asking you to find critical point, you will have an example where there's one of each, like a corner where it's not continuous and where there's a vertical tangent. But in this example, there's none of them. So critical point at 0.8, at 2, and at -1. And now let's find like where it's positive and negative. So let's find where f prime is bigger than 0 and where f prime is less than 0. And normally I just do it right away. So from -infinity to the first critical point at -1, the function is going up. And if you pick any point between -infinity and -1 and you draw the tangent, so I'll just do an example here. So if you pick any point and you draw the tangent, okay, you're going to get, of course, a line that is going up. So the f prime is strictly positive. So here from -infinity to -1, it's going up. And then between -1, so between critical points here, so remember I have one at 0.8, so pick any point between between -1 and 0.8. If you draw the tangent line there, you're going to get, oh my God, you're going to get a line with positive slope. So again here, so between -1 to 0.8, my slopes are all strictly positive. And now between 0.8 and 2, my slopes are going to be going down. Oh my God, it's a little room here. Okay, so there we go. Okay, so it's going down. And so we have our first interval where it's going down. So between 0.8 to the next critical point, that corner, 2. And then from 2 to infinity, pick any point here. Any tangent line will be, of course, going up. So here, finally, from 2 to infinity, my function is such that the slopes of the tangent line are all strictly positive. And of course, where it's strictly positive, it's increasing. Where it's strictly negative, it's decreasing. And that's for, okay, our visual examples, like the link between critical points and its visual representation. So horizontal tangent for f prime equal to 0. If you have a corner or a point where it's discontinuous, or a point where the slope, the tangent line is vertical, you have points where f prime does not exist, or where the function f prime is undefined. And if you have that f prime is strictly bigger than 0, then your function is going up. If f prime is strictly less than 0, then your function is going down. And you should be able to find those intervals visually. Okay, so if you have a function defined graphically. And now that's it. That's all for that video. And it's actually the end of the videos for that chapter. There's another chapter with more examples, but you can just do them as a set of exercise. But for chapter 4, that's it. That's all for real this time. Okay. Bye-bye, the end. Okay, the end of chapter 4. Bye-bye.